是文东林嘛？你是文东林，你是不是比较迟 enroll 啊？
是
为什么啊？
这个应该下一个，但是好像后面发现不太感兴趣。
又回来数学？
对，
不然金瑞不是没有朋友啊
有啊，其实有好多朋友。
？OK OK，我记得你们不是一起每次睡
我跟他是
啊？
In the back, see the front, do you need to turn off the light? It's okay? Okay, okay. Okay, before we start, okay, good morning everyone. Before we start, let's deal with some admin work first. I have posted the lecture one again with the solution. You should see it on Moodle now. And it's 端天吃 here. 端天吃. Not here. 端天吃. Okay, never mind. Okay. Another thing is my office hour. Wait. Somehow my pen is not connected. Let me restart my iPad. So one thing I want to ask is, because my office hour used to be Tuesday, right? Except Tuesday, but someone request to change to Friday morning. Are you guys okay with Friday morning? Okay, everyone okay? Okay. How about 8:30? 8:30 until 12:30. You guys prefer to split the office hour or in a block? You get what I mean? Split. It's okay. Okay. So one block Friday, 8:30 to 30. Or you want earlier 8 o'clock? 8:30. Okay. 8:30 until 12:30. And you will see me in my office. You don't need to come for the full 4 hour. You just need to come any hour. Feel free to drop in. You guys want to start tomorrow or next week? Is someone coming tomorrow? Tomorrow. Okay. I only go office if you come. Okay. And then next week we will start Friday also. So I'll update the course information as well. Okay, tomorrow 8:30 to 12:30 I'll be in the office. I'll see you if you need. Any question from yesterday or from that tutorial that you do? Anything you want to ask? Please use the forum I posted. Okay. If you have any issue, just post on the forum and then we will look at it. Sign in. Okay. So let's pick up from what we finished yesterday. So let's recall. Recall what's the linear transformation. Okay. So linear transformation is a function or is a transformation. Okay. We denote it as a P. Okay. It's a function from the domain Rn to codomain Rm to be different, such that two conditions satisfied. Okay. So the two condition is one, it respect the vector addition. Okay, so if you apply to a vector addition, it's the same as you apply separately and then you add the vector. Okay. Second is if you apply to a scalar multiple of a vector, it's the same as if you apply to the vector and then do the scalar multiple after. Yeah, these are the two conditions it satisfies for all scalar. So why we are interested in this kind of transformation? Because there's a theorem say that all linear transformation actually matrix transformation. So you can just use matrix to calculate the linear transformation. So when you apply a transformation, it is just like you take a matrix and apply to the matrix. Okay. So for example, maybe look at the example first, then we go into proof. For example, so yesterday we see that if you're trying to scale the vector, okay, if you apply a linear transformation that scale the vector, okay, everyone can see it. Okay, it's just apply the a scalar multiply a identity matrix. Okay, then you will scale the vector by the factor of r. Remember from yesterday. Okay, so linear transformation can be realized as a matrix transformation. Okay, so first thing you will see that is all matrix transformations linear transformation. Okay, so meaning the map x go to ax is linear. Okay, so linear transformation satisfy how many conditions? Linear transformation satisfy how many conditions? How many conditions? Linear transformation satisfy how many conditions? Linear transformation satisfy how many conditions? Right. Okay. So one in respect the vector addition, and then second in respect the scalar multiplication. Okay. So to say that matrix transformation is linear, you need to check that ax plus y bar equals to ax bar plus ay bar. Okay. Second, a applied to cx is equal to c times ax bar. Yeah. Make sense? So you could check that actually matrix vector multiplication actually satisfy these two conditions. Okay. So the matrix vector products okay. Second is you could ask if I give you a linear transformation, for example, rotation, okay, or translation. How do you write down the matrix? Okay, how do you find the matrix? How do you find the matrix? Okay, this is the question we will address today. So the second part of this proof is this one is the first part. The second part is given a linear, I just tell you how to change the vector. How do you give me the matrix? Okay. To obtain the matrix that describe the transformation. Okay, so today we will address this question. Given a transformation, how we find the matrix. Okay, any question for now? Up to now? No. Okay, next. Okay, next. Let's try some example first, okay? Let's see. Let's say we have a linear transformation, okay? And then we know how the function, okay, send these two vectors here. Can you figure out the matrix that multiply to 1, 0, that you get this column vector? And when you take the matrix, when you take the matrix A, when you multiply to 1, 0, you get 5 minus 7, 2. And then when you multiply to 0, 1, you get minus 2 and 0. Okay? Maybe spend 2 minutes. Okay? Try and think about how to come up with this matrix. If I just tell you these two pieces of information, can you come up with a matrix? A. Okay. Can anyone tell me what's the size of the matrix first? What size do you need? 3 times? 3 by 2, okay? Because it's a map from R2 to R3. Okay, so A should be a 3 by 2 matrix. 3 by 2. So what's the first column is? I'll get the first column. What's the first column? Anyone try? 2, 1, 2. You mean this one 2, 1, 2 is again second column? Huh? Sorry? Oh, not found yet. Okay. Okay. Let's say you haven't found yet. Okay. Let me put something like this. Okay. Not found yet. Anything. Let's apply this A to 1, 0. What happened? What do you get? What do you get? You get 2 plus anything times 0 is 0. Okay. Let's use the matrix calculation we learned this time. So it's 1 times the first column plus 0 times the second column. Right? Okay. No matter what you put in the star, this will become a 0 vector. So what you left with is 2, 1, 2. Okay. But I want 1, 0 get sent to 5 minus 7, 2. Okay. So what should you change the first column to? 5, 5 minus 7 and 2. Okay. So you should change the first one to 5 minus 7 and 2. How about second column? minus 3, 8, and 0. Okay. So you could see that these two are special vector. Okay, 1, 0 can read out the first column, and then 0, 1 can read out the second column. Okay, so then these two will determine the exact matrix you need. Okay. So the question asks about find Tx for any x. So you just write Tx is equal to Ax, which is equal to 5 minus x minus 7, 8, 2, 0, time, maybe you put xy, okay, and then you will get what's the right, minus 3y minus 7x plus y, 2x plus 0, 1. Okay, that's it. Okay, so you need to have given you a linear transformation, find the matrix. Okay, so how do we generalize this to general cases? Okay, so in Rn, we also have this something look like the pivot column. Do you realize? So anything below 1, above 1 is 0. Okay, so this actually there's a name for them. We call it a standard basis. Standard basis in Rn. Okay, so it's a 1 at a different spot. Okay, so if it is EI, is in the first spot, E2 in the second spot, E3 in the third spot, and so on. Okay, so these are the special name, special function. Okay, so the theorem is if I give you a linear transformation, then there exists a unique m times n matrix. Okay, not that this m and this n is connected to the nm here. Okay, such that Tx equal to Ax. So how to find the matrix? In fact, you just need to check. So we won't prove this. We won't prove this. So the main takeaway is get your linear transformation and let Tx on EIs. Okay? Add on all the EIs. Okay? Add on all the EIs, then you will get all the column of your matrix. Understand? Understand? Okay. So this EI will follow the for I ranges from 1 to the dimension of your whole domain. Sorry, your domain. Okay. Okay. So why is it enough? Because really this standard basis will span your domain. So everything in the domain can be written in terms of EI. So you just need to care about where EI gets sent. Okay. So if you forgot, you just go back and study this example again. Okay, study this example again. Okay. Any question? Any question? Everyone know how to get matrix A? Okay. Question. By the way, if is Duan Tianzi here? If not, second hour I ask again. Okay. Any question? No? Okay, let's keep going. Okay, second. Okay, let's don't review these to you first. Okay, second, because this is a function, okay, we want to know two property of function, two main property of function. One is onto, one is one to one. Okay, I believe discrete math student should have seen this before. Okay, onto one and onto. So a mapping or transformation, okay, a linear transformation. Okay, all familiar. A transformation is said to be onto, okay, onto to the core domain if for every element in the core domain, okay, there's at least one x get mapped to the from the domain mapped to the core domain. Okay, so that means for everything in Rm, so let me draw the picture for you. So given the transformation from Rm to Rm, and I pick anything in Rm, I can find a guy in domain get mapped to y by t, such that y equals to dx. Okay, so this is onto because you want to like onto the space. So everything from the core domain, I can find someone from the domain that matches. Okay, get this idea? Okay. So from this picture, you can see that, okay, if Rm is a square, is this not square, this is a cube, okay, a box, okay. If it is onto, then it will occupy all the box. Make sense? Although this is not a box, I think. Okay. Yeah. So the idea is you can reach everything in the core domain if it's onto. Okay. Any question? No. Okay. So this is onto. Next is one-to-one. Okay. So a mapping or a transformation is said to be one-to-one if every element in the core domain, let's jot this down, core domain, is the image of at most one element in the domain. Okay. So it can't be two different elements get sent to the same element. So this is not allowed. Okay. So you cannot have two different elements get sent to the same element. One domain, one element in the domain only can match with one element in the codomain. Okay, make sense? Okay. So what does this have to do with what you have learned before? Okay. So actually, this is a new description of the existence and what? Uniqueness? Unique. Okay. Why? Okay, why? So, where should I write? Okay, let's write somewhere here. So we know that a transformation, okay, a transformation can be realized as a matrix multiplication. Okay, matrix multiplication is a matrix vector, right? Okay, so let's see what is going on here to present to you. So let me show something. I cut it first. Okay. I cannot cut it. Okay. So let me just reproduce everything then. Okay, so let's talk about onto first. Okay, so onto mean for every v, let's talk about the function from Rn to Rn. Okay, a linear transformation. So this means for every b in Rm, okay, I can find an x in Rn such that Tx equal to Bn. Okay, everything in the codomain, I can find one element in the domain get matched to. Okay, because onto, I can reach every guys in the codomain. So, but we know that every linear transformation we can realize as a matrix multiplication, right? So here, what we have achieved here is linear transformation, transformation realized as a matrix equation, right? Okay, so in matrix equation, if we can find the solution for the linear system for any b, so what does it mean? So that means you can find solution. Remember the theorem? If we can find a solution, then there's the four equivalent condition we have. Who remember the four equivalent condition we have from yesterday, the theorem? If we can find a solution for the matrix for any b, what was the four equivalence? Anyone can remember? Anyone can remember? Let me just write it out. So one, A has pivot column in every row. Okay. Two, the column of A span Rm. Okay. Every element B in M is a linear combination of the column of A. Okay. And then the last one is exactly this condition here. Right? Okay, you can find a solution for every b in your codomain. So we turn around, change the question again, and again in different way. Actually, this should be our last stop. Okay. Actually, what we care about is linear transformation. So previously, we just simplify the linear transformation problem to raw reduction and so on. Okay. So what we really care about is linear transformation. We care about function between spaces. Okay, and then we want to solve problem on function between spaces. And then what we did in the first class is just a tool to study. Okay, so that you can't see the picture, but in the end now you will see the picture. It's actually a function between spaces. Okay, so this one is really where we aim for. Okay, how about onto? So this one settle the existence problem. And how about one-to-one? Okay. So you should guess that one-to-one should be related to uniqueness. So how is it uniqueness? How it connect to uniqueness? So what's uniqueness means? Do you have infinitely many solutions, or you have only one solution? Right. So uniqueness means you only have one solution. Okay, the question. So one-to-one says what? Also, we start with a linear transformation. Okay. So what is one-to-one? Make sure I follow. Yeah, maybe I give another formulation for one-to-one. Okay, maybe not. Later I confuse you. Okay, let's use what it is stated here. So for any B in Rm, okay, I can only find one, at most one. Yes, at most one. So I can find or I cannot find. Okay, so that's why I put at most one. Either I can find, either I cannot find, or if I can find, there's only one I can find. So at most one. So this one is actually means less than equal to. Okay, at most one solution to what? To the equation ax equal to b. Okay, or if you like, we can study tx to b first, and then through the equivalence, we can find the matrix equation. Okay, so this means either it is inconsistent, we cannot find solution, or we can only find at most one. So only one I can find. I cannot find more than one. So this means the solution either it exists, either it doesn't exist. If it exists, it is unique. Okay, make sense? Okay, makes sense. Okay, so let's see how we gonna play around with this thing. This one is okay. So let's see how we play around this. So let's look at this question here. So as usual, we start with a linear transformation. And this time, it doesn't tell you how you add on the standard basis. It straight away gives you the matrix. Okay. Yeah. Okay. Save the work. So the question is, does this linear transformation map R4 onto R3? And the subsequent question is if T one-to-one mapping. Okay. Mapping is the same as transformation is the same as function. Okay. It's just different nouns. Okay. So first of all, check first, is it the right domain and codomain? So this size is what? A is what size? The matrix. What's the size of matrix? 3 by 4. 3 by 4. Okay. So it's a 3 here and then 4 here. 3 by 4. So you map 4. You map 4 to R3. R4 to R3. Okay. This is how we read it. This is correct. So the right domain and right codomain. So recall what is the definition of onto. So every let me change to so for any B in the codomain, okay, in the codomain, this one is codomain, this one is domain, okay. Let's write it on. For every element in the codomain, we want to find X bar such that Tx equal to B hat. Okay, right? But Tx equal to B hat is equivalent to what? Ax equal to B hat. So is this familiar for you now? This is the matrix equation. Okay. So, so what's the next thing you do? Once you got a matrix equation, what's the next thing you do? What matrix you can get from matrix equation? Oh, the augmented matrix, right? Remember? Okay. So you can set out your augmented matrix now. So what do you put as your constant vector here? What do you put here? What's the B here? You know what B is in this case? You know what's B here? Here. What's the B here? Okay. So there's no specific B here. Okay. Because B is any vector in Rn, R3. So you could just set it as some variable. For example, write B equals to any vector here. Okay. And then you try and solve this. Okay. Try if you can find an X that satisfy the matrix equation. Got it? Make sense? Okay. Any question? No? Okay, let's try and solve this together. Okay, so this is not reduced yet, but already a row echelon form, right? You can see it? Okay, because everything below the leading entry is already 0. Okay, and it is already step-like, like an echelon. So what you do next is you need to make them the pivot position. So you need to make everything above 0 and then make the leading entry 1. Okay. So what's the thing we want to do? Okay. Okay. Uh, okay. Just do first. Okay. Later I will tell you a secret. Okay. So 1 over 5 R3. This is what I will do first. 1 minus 4, 8, 1. And B1 minus 1, 3, B2, 0, 0, 0, 1, B3 over 5. Please help me to check my calculation. So what you want to do next is the backward phrase, okay, of the row reduction algorithm. So I want to make these two 0 first. Okay. For the time, for the sake of time, or maybe you can do in exam as well. I do in one go. Okay. So I will do R1 minus R3 and R2 minus R3 R3. Okay. But be careful when you do this. You don't overlap your working. Okay. Actually, I separate these two. I combine these two. But be careful when you do this. It might be wrong sometimes because you mess up. Okay. So what I get is B3 over 5 minus 2 minus 1, 0. And then B2 minus 3 over 5. Please help me check my working. I'll keep doing first so that I get the answer. And then what I will do next is I will 2. Okay. Sorry. Here I'll get 0. And then 8 minus 2 I'll get 6. And so I get 0. Get B1 plus 2B2. And then I will get 6, 7 minus 7 over 5 be 3. And then 0. And then 2 minus 1, 0. And then 2 minus 3 over 5. Then 0, 0, 0, 1 be 3 over 5. Again, the last step is to make the 2 into half. So what do I get? 0, 1, negative half, 0, and then half be 3. Oh, very messy. Getting messy and messier. Mathematicians don't like this kind of number one. Very messy. We don't like this kind of number. Okay. And then okay. So from here, can you bring out the solution now? Okay. So you get x1 is equal to minus 6, 3 plus jump here. And then x2 equals to half x3 plus another jump. And then S3 is 3. Free. Okay, it's free. S4 is equal to B3 over 5. Okay, so you can see that you can find a solution. Actually, we don't need to spend this much of work doing this, right? Because remember the theorem, if we have a pivot solution, pivot position in every row, that means there's a solution to this vector, the matrix equation, right? Just now I remind you. Yeah, this one. Okay, so actually you can just stop. Yeah, yeah. So this is the secret I want to tell you. You don't need to go through all this property. Okay, as long as you can find the pivot, unless the question asks you about the pre-image. Okay, ask you to tell me specifically what's the thing get mapped to. Okay, then this is a different case. Okay, next is how about T? If it is 1-to-1, okay, if it is 1-to-1, so everything that it get maps to, is it more than two different things get mapped to the same thing? Okay, what do you think? Yes or no? Yes or no? Yes or no? Yes or no? Do you have two different things get mapped to the same thing? What do you think? Hmm? What do you think? Do you have two different things get mapped to the same thing? Yes or no? Try. Yes or no? Maybe not. Why? Xin Peng say no. Why? So why is it not? Do you have idea? No idea. Okay. Sure. But luckily, we done this calculation here. Okay. So if it is the image of your function here, okay, you can see that there's a free variable here. Okay? Meaning if I change any free variable, any number, I will map to the same number. Okay. Right. So if there's a free variable here, you have more things get mapped to the same number. Or you can just come up with two vectors that map to the same place, but they are different. Can you come up with two vectors that map to the same place or not? Okay, first settle the first question. So T maps R4 onto R3. Okay, so the second question is, it is 1-to-1. So my claim is it is not. Okay, from the calculation, we can see that there's a free variable. So free variable, I can put any number such that I get the same solution. So another way to prove T is not one-to-one is to find two different vector that have the same image. Okay, can you come up with two? Can you come up with two? I can. Okay, so let's try 5, 0, minus 1. Sorry, 5, 0, 0, minus 1. And 1, 0, 0, minus 5, 1 fifth. Okay, can you see what A or what linear transformation send these two vectors to? Oh, sorry. Sorry. Cannot use these two. Can I come out with two? I just impromptu and see. Again, that easy. This question, because this question this part here very weird. So I think okay. Since it is not so easy, let's leave as the homework. Okay. Okay. Try find these two different vectors. I will find as well. Okay. Next week we can compare. Okay. Try find the two different vectors. Okay. That map to the same image. Okay. One tips I give you is try find a vector that gets sent to zero. Okay. My claim is they will have two different vectors get sent to the zero vector. Okay. Okay, try find the two different vectors that get sent to zero. One, of course, is zero. Okay, so I already settled half of the problem for you. One is zero. What's the next one get sent to zero? What's the next one? The next one. Okay, I cannot see it now. And next, maybe next hour I can see it. Let's see. Okay, I leave it as a homework for now. Try find another x that get mapped to zero. Okay. Okay, let's see. If cannot do that, then maybe it is one-to-one. And then we will see it again next time. Okay, next. Why am I claiming that? Because we have this theorem. Okay, this theorem says that T is a linear transformation. Then, if T is one-to-one, if and only if Tx equals 0 has the only solution. Has the only trivial solution. Okay, so trivial solution means x equals to the zero vector. Okay, some of you, when I have some conversation with you, sometimes you confuse the solution with this part here. Okay, whenever we talk about solution, we care about this x here. Okay, this is, although this is equal to something, in some sense it's a solution, but the solution we're talking here is this x here. Okay, this part is the b part, the constant vector part. Okay. Okay. So do you want to prove this? You want to see a proof, or the proof is not too hard, but do you want to see? No. No. No, don't want to see. If you don't want to see, then you need to accept the fact that if you want to check something is one-to-one, you just need to check that this has a trivial solution. Maybe I'll show you the example first. Do you want to see a proof or not? No? Yes or no? Just yes or no? Yes. Okay, someone say yes. Yes or no? Okay, I see raise of hand. Who want to see the proof? Over half only I can do the proof. Okay. Yeah, about half. Okay, if you want to see the proof, okay. So there are two directions here, right? If and only if. Okay, so t is 1 to 1. If and only if tx equals 0, that's only the trivial solution. Okay, so there are two directions to work. One is forward, one is backward. Okay, so which one you want to do first? Maybe we do forward first. I forget which one is easier, but let's do forward first. So suppose t is 1 to 1. Okay, and what we want to show? We want to show that tx equals 0 has the only trivial solution. Wow, I left out all my I. We want to show that tx has the only trivial solution. Okay, which means t0 equals 0 only. Okay. Okay, so since t0 equal to 0 for any t, you know why? Because a0 is 0. Okay, makes sense, this part? Because every t I can realize as a matrix, right? So a matrix times a 0 vector, what do you get? 0. Okay, and b. Since t0 equals 0 for any t, and t is 1 to 1, 1 to 1 means what? Every b in your codomain, there is at most one x such that tx equals to b. Okay, so if you take your b as 0, okay, there's only at most one solution that solves it. You already found 0 as a solution, so only 0 can be the solution. Can get it? Can get it or not? Any question? Any question? So since t0 and this one, we have, wait, let me change it. We have 0 as the only solution to tx equals 0. Okay? Okay. How about the other direction? How about the other direction? The no space to do. Let me take over this space and then later we'll move it away. So let's use this space here first. So suppose the other direction is suppose tx equals 0 has the only trivial solution. Okay, we want to show t is 1 to 1. That is what? For every b in the codomain, okay, we have at most one x in the domain such that Tx bar equal to Bn. Okay? So suppose it is not. Suppose for the sake of contradiction, it is not. Okay? Suppose for the sake of contradiction, T is not 1-to-1. Okay? That's mean what? That's mean that is. Should I use contradiction or not? Maybe I don't want to use contradiction, later I confuse you. Because if I use contradiction, right, there's some logic I need to use. Okay, because I don't teach the logic in here. Maybe discrete math will know, but I try to avoid this. Okay. I avoid this. Okay, I avoid this. Okay, just be straightforward a bit. Okay, straightforward a bit. So suppose Tx equal to B hat and Ty equal to B hat. Okay? Okay. For some, I don't know what is X, what is Y, just something X, something Y. Okay, in my domain. What you can do, you have two equations. How you play around with two equations? Add or take away, add or minus them. Okay, so you can minus the two equations. Okay, this is what we learn all this on it just today. Okay, so we can take 1 minus 2 or 2 minus 1, up to you. We can take the difference of the two equations so that we get Tx minus Ty equal to 0. Right? B minus B. Okay, so what we can do is, because this is a linear transformation, right? So we can collect the T. Okay, respect the vector addition. Okay, but remember what's the assumption we have? Suppose Tx equal to 0 has only the trivial solution. Okay, that means this equation have the trivial solution, meaning by assumption x minus y bar equal to 0, which implies x equal to y. So you only have at most one solution. Okay, after I prove all these things, right, make sure you know how to use this theorem. Okay, so now we will use this theorem. Any question on the proof? Any question on the proof? Should be quite straightforward, nothing special here, but yeah, so I want to challenge the discrete math student. Can you prove this part using contradiction? Yeah, if you do it, you can show it to me, email to me. Okay. Okay, next, let's try this example using the theorem. So let me move all this. Okay. What time is it? 10 o'clock? Wow, so fast. Let's see. Let's finish this and then we have a break. Okay. Okay. So you want to show that if this is 1-to-1, okay. On to I leave it as a homework, okay, because this is what we did just now. But let's try 1-to-1, okay, because we want to apply this theorem here. So the theorem say it is 1-to-1 if the equation Tx equals 0 has the only trivial solution. So you need to check whether Tx equals 0 have the trivial solution or not, right? Okay, so what do you do? Can you transform T to the matrix first? Can you get what is A? Any idea what is A? Any idea what is A here? A is a what size? What size of the matrix? What's the size? 3 by 2. Good. Okay, so what's the first column? 3, 5, 1, 1, 7, 3. Okay, so you can see that they change the notation of the vector. Okay, so but don't confuse. Okay, don't confuse. So this one, this notation is the same as this notation. Okay. Okay. So now you want to solve. Okay, what is this? Okay, this is different. Never mind. So you want to solve if tx equals 0 as the trivial solution. Okay. So what's your augmented matrix? You get 3, 5, 1, 1, 7, 3, and 0, 0, 0. Okay. So do we want to solve it? If anyone solve it? Yeah. Okay. Let's solve it. So make it smaller first. Okay. So what would you do? This is I get the 1 out first. So R1 change with R3. 130315700. Okay, and then I make everything under the first pivot position 0. So R2 minus 3R1. Okay, and then R3 minus 5R1. Okay, make sure these two operations don't overlap before you do. Okay, so so I get 1 0, and I get 0 9 1 minus 9 minus 8 5 minus 0 7 minus 15 minus 8. Is it? Yeah, minus 8. Okay, and then what do you do next? You can do 3 minus R2. Okay, then you get 1 3 0 0 0 0 0, and then I will scale the second one. What I get is 1. Okay, and then I make the second pivot position, so I need to remove the 3. On the 3 is very easy to remove. So I will get 1 0 0 0 1 0 0 0 0 0. Okay. So the solution is x1 equal to 0, x2 equal to 0. So this is the only trivial solution. So T is criteria. Okay. Any question? Any question? So let's complete it. Hence, the trivial solution is the only solution to Tx equals 0. And since f t is equal to 1. Okay, this is how we use the theorem. Any question? Any question? Okay. Yeah, let's break until 10:15. Okay, let's break until 10. 啊
Is the sales carrying still there? For this case.
I can later I will mention again. Yeah.对，哦，昨天讲那个不太明显，以前
就是你说那个，就是能找一个零的，就是除了这以外，还有可以是它。
啊，对啊，对呀，没错，
但是呢，他找不到也是，实际上他就是就没有这个，
找不到，
就是只有是全部是零。
is there than such yes，没有其他的解是吗？there more than such x，对，因为通常有的话会直接出现，
这个已经都已经写出来
对，
了，没有
给我
两个零
想一下，
的。
想一下，哦，因为它这个是，嗯，
就把这个
对，
这个地方改
换成零，
成零的话，
对
也是
对，
解法就是
对，嗯，因为其实这个东西是 one to one，刚才我们说有点像，其实这个东西是 one to one，对，因为另外一个解的话就零嘛，
对，
嗯
所以其实还是只有一个。
，OK，等一下我会改一下，这是昨天的东西，那我也改一下，OK，其实还有一个啊，OK，
对，这个也是，
你说怎么做啊？
就是不知道这个它这个 A 指的是什么？
呢，这里 R 就是什么 A，啊，R 就是什么 B，
哦，就是指这边是
等一下我会改，
温度是这样，那符合就符合那个，所以它就是温度。
不是，这个 equivalent 是为了算这个 linear transformation，但是 equivalent 那个 onto 是这一个，
嗯，
每一个 b，
是那个 solution 像这样子。
嗯，
如果它找不到，就是 inconsistent，所以它不是 onto。
哎对，啊对，翰林旁边那个叫什么啊？翰林旁边那个，是它不是有个零，旁边那个叫什么我忘记了，也是 DMT，
对，
翰林旁边那个白色一页，这边，这里，现在叫什么名？这叫什么名？翰林旁边那个，记得翰林，他叫什么啊？我忘记了啊，叫什么？玉，听到没？心源啊。哦，OK，今天 OK，是这电梯。 Okay, yeah. Let's come back to this question, right? Actually, I realized that I prophesied wrong here. So this is actually 1-to-1. That's why it's so hard to find the two. Okay, so how to see it is 1-to-1. So you just make the same calculation by putting here 0 all the way. Okay, and then you can see that everything here is still 0. Okay, and then if you row reduce it, you row reduce it, what happened? Okay, let's try, okay? Let's try. Let's see what's going on. Okay, let's put back again. Let's check again. Let's check. I still want to get this done. So let's try it. Okay, let's try the last bit here. Engineer this bit. Okay. If we set B1 equals to 0. Okay, what do we get? Okay, 1, 0, 6, 0, 0, 1, and 0, and 0, 0, 0, 1. Okay. This side is a 0. What solution we get? We get x1 equals to x3, and then x2 equals to what is x3, and then x3 is 3, and then x4 is 0. Okay, I think we can see now. So first thing you can put is 0, 0, 0, and then second one you can try out is -6 half 1, 0. Okay, let's try. Does it work? Let us copy down the actual matrix A. So what's the matrix A? A equals to 0, 0, -4, 2, 0, 8, -1, 0, 1, 3, 5. So it's A times the second vector 0. It should be 0, but let's check it out. -6 half 1, 0. Is it 0? Is it 0? Is this 0? Is this 0? Is this 0? Okay, let's try this. So this is minus 6 of 100 plus half of. Okay, maybe don't do this. Maybe just combining. So minus 6. Zero plus 2 minus 1 0 and 0 0 0 0. So this one is 2, this one is 1. So minus 6 minus 2 plus 8 0 1 minus 1 0 0. Okay, so I managed to find two different vectors that get mapped to 0. Okay, so T is not 1 2. Okay? Because two things get mapped to the same thing, so it's not 1 2. Okay, any question? No. It's 端天之 here. 端天之. Okay, never mind. Okay, let's pass this down and then okay. So just now Xing Yan come to me and talk about the yesterday questions. Said I made a mistake around here. Okay. So the question is, does this linear transformation here has more than one x such that the image is B? Okay. So B is this vector here. Let me remove all this nonsense. Okay. So find one x such that Px equal to B. Okay. And then yesterday what I said is if you row reduce this, if you take this and add up the solution for the homogeneous equation, you still get a new solution, right? This is what we learned yesterday. But it turned out the solution to the homogeneous equation is only the 0 vector. Okay, which you can straight away see from the calculation here. Because to do the homogeneous equation, you just replace the vector b with 0, right? And then the row reduction is still the same. You can row reduce to this, and then you get 0 0 0 here, where you get x1 equals 0, s2 equals 0. So 0 vector is the only solution to the homogeneous equation in this case. So what this means is there's only one x here. Okay. So this one is wrong. There's only let me change the color. There is only one x such that Tx equal to B case. This case, since only the trivial solution solve the homogeneous solution. The homogeneous system. Okay, which means this function is actually 1-to-1. Okay, from what we learned today, actually this linear transformation is 1-to-1. Okay. Okay. You want to take picture? Yeah. Okay, very good. So try don't just accept what I say. Okay, try and question me. Any question? Any question? No. Good. Okay, so we pick up where we stopped just now. Okay, so so the next theorem or summary, actually this is the summary. We won't prove this again because this is just a summary, but phrase it differently. So we already provide way for you to check something is onto and one-to-one. Okay. So let's start with a linear transformation again. Okay. By the theorem, we can find the corresponding standard matrix, the matrix for T. Then, okay, one, T maps onto to the codomain. Okay, we can reach every codomain by the pre-match if and only if the columns of A span Rm. Okay, this one, remind you, is the theorem of for equivalent statement we stated in the class at the start of the class. Remember? Okay, this is coming from there. B is just what we have done. T is one-to-one if and only if the columns of A are linearly independent. Okay. Okay. This is what we have just done, but we're not stating it in this way, right? Because just now we said what? Let's put here AX equal to 0 has the trivial solution. Okay. Remember, matrix equation is the same as the vector equation. Okay. So vector equation is what? Is the column of the matrix. This is the equation that we determine whether it is linearly independent or not. Remember? Okay. So everything are equivalent. So look back the notes. Okay. Can see or not? Cannot see? Can see? Sorry, can see. Okay. So if x1 up to Sn is the only zero vector. Okay. Remember, if it is all zero, there's no relation between the vector. If there's non-zero, then there's some non-trivial relation between the vector. Okay. So there's no relation between the vectors. So the columns are linearly independent. They are independent from each other. There's no relation between the column vector. Okay. Okay. Yeah. If not okay, you should point out. Yeah. If you're interested, you can go and look for the proof in the book. Okay. Okay, next, matrix operation. Okay. So there's some not lie, but something I didn't tell you. Actually, vector is also a matrix. Okay. So matrix, what is matrix? Matrix, an m by n matrix can be written as the size of m times n, and then you can label your entry by A11, A12 until AIN, A1n, and then go down is 1, 1, 2, 1, 3, 1. Go down a column is 1, 1, 2, 1, 3, 1. So what I'm saying is the I will control the row, J will control the column. Okay, so this is in accordance to the arrangement of M and N. Okay, so I is going from 1 to M, and then J is going from 1 to N. Okay, let's make it bigger. Okay. Then so in this case, vector is a M times 1 matrix. Right? Vector is a M times 1 matrix. Saying is a vector in Rm is a M times 1 matrix. Okay? Okay. M1. Okay. Vector in Rm is an M times 1 matrix. Okay. So now we looking at a matrix operation. So this one is the row description that we use to. Okay. So we can split this to row. So note that there's the abuse of notation here. Okay. Meaning we don't really look at it like this. Okay. Although it might mean something like this. Right? Because you put a bracket, square bracket outside the vector. Okay. Although it means something like this, but actually this is an abuse of notation. Okay. So what I'm saying is this is a abuse of notation. What we really care is this row, this column of numbers. Okay. Okay. We don't draw like this. We don't draw something like this. Okay. If you care about matrix in a matrix, that thing is called a tensor. Okay. Matrix is called a tensor, but we are not dealing with that thing. Okay. Okay. Some particular matrix. One is the diagonal matrix. Okay. Diagonal matrix meaning there's only non-zero entry on the diagonal. Okay. And everything else is 0. So every number is on the diagonal. Okay, so this is a diagonal matrix. Diagonal matrix have some interesting property. Next is identity matrix. Identity matrix is a diagonal matrix with entry 1 on the diagonal, okay, and 0 at the other places. Okay, so you can see that this one is actually the combination of standard basis. Okay. Combination of standard basis. Next interesting one is the 0 matrix. Again, this is the thing, this is the identity matrix. Okay, 0 matrix is everywhere. Is 0 everywhere? Okay. Okay, something to note here. Diagonal matrix and identity matrix have to be square. Meaning m times n, m have to equal to n. Okay. You cannot have something like this. Then this is not an identity matrix. Okay. So it must be equal m and n. It's a square. Okay. Diagonal matrix similar. 0 matrix can be different size. M can be not equal to n. Okay. Next, mathematics is like this. We got one thing, we want to combine things on. Okay. So how to combine two matrices? We can add them together, just like adding the vector. Every entry has to add to the same entry. Okay. So what does this mean? You cannot add different size matrix. Okay, if you have different size, the extra guy, who do you add to? I don't know. Okay, so it's not immediately not yeah. So you only can add same size matrix so that you can compare one by one. Okay. Secondly is scalar multiple. It's also the same. Multiply each entry with the same number. The easiest thing you can do. Okay, it's just like a vector. So in this case, matrix become a vector again. Okay. Yeah. So matrix become a vector again. Okay. So some exercise you want to try. Okay. Okay, I let you try. 2 minutes, give me the matrix. Can see? Everyone can see, huh? Anyone got it? Just shout it out. Okay. Got it? Got it? What was the first column? In 10. Okay. 8 minus 3. And then 1, 7. Okay. Okay, good. Everyone got this? Hey, what's the second column? Second column is what? Minus 3 and 0. Okay. Everyone got this? Okay. On the same page? Okay. Just similar. Okay, good. Okay. So you can see that this is the similar property that shared by the algebraic, not algebraic, sorry, is the uh, properties of addition, vector addition, the addition, and scalar multiplication. Okay, so really matrix is also a vector. Okay? It's also a vector. It's just that we don't put it as a line, so we put it as some array, right? Imagine. So for example, like 3, 4, 5, 6, 7. Why not we turn this into 2, 3, 4, 5, 6, 7, right? Okay, so not much different, just that we put it differently. Okay, but once we do that, we can do more interesting stuff. We will see later. Okay. Okay. Next, this is the thing that vectors cannot do. Okay. Last time we say that we cannot multiply. How to multiply two vectors together? I mean vectors in Rn. Okay. Or in this case, I should say the m times 1 matrix. How we combine these two? Okay. There's no natural way to do that. Of course, you have cross product, dot product, but those, yeah, of course you have dot product, cross product, but there's one natural way for matrix multiplication where if you have an m times n matrix and an n times p matrix, okay, you can combine them. Okay. How you combine them is you do the row times column business. Everyone learned it or not before this? So for example, let's use example to study this better. 7, 8. Maybe too big. Make a small number. Okay. So you need to make sure this is 2 times 2 and 2 times 3. So you need to make sure these two is the same first. Okay. Only then you can do matrix multiplication. Okay. So maybe make different color so that it's not a scalar, it's just a size. So what you do is to get the first entry what you do is you take the first row times the second column. Okay, and then how do you do that? You take the first entry, multiply the first entry take the first entry in the row and then multiply with the first entry in the column, add up with the second entry in the row, and then multiply with the second entry in the column. And then to get the rest, you will take the first entry, first row times the second column, where you get 1 times 0 plus 2 times 1. And then to get the rest of the first row, you will take the first row again, multiply a different column. We get 1 times 1 plus 2. Okay. And then the second row, how do you get the second row? You take the second row from the first matrix and then multiply with the first column, second row with the second column to get the second term, and then second row with the third column to get the third. Okay. Okay. So this is what this compact notation about. Okay. Any question? No. Yeah. So let's find A, B, and BA. See if you can do it. So first you need to check the size first. So A is a 2 times 3, and B is a 3 times 2. Okay. So 2 times 3, 3 times 2, 3 is the same. So we can multiply together. How about BA? 3 times 2 times 2 times 3. So 2 is the same. You also can multiply together. So AB is the size of what matrix? 3 times 2, 2 times 3. So you take the first and the last number. So you get a 3 by 3. BA, you get what? 2 by 2 by 2. A is a 2 by 2. Sorry. AB is a 2 by 2. Sorry. So this is a 2 by 3. This is a 3 by 2. So you get a 2 by 2. Okay. And then this is a 3 by 2. This is a 2 by 3. So you get the 3 by 2. Okay. Okay, let's see what you get for the matrix very quick. Anyone got the answer yet? Everyone try? Anyone got it? Maybe some of you can compute AB first. Some of you can compute A first. Okay. Which one you get? AB? AB, what is AB? Minus 33. Seriously, minus 33, and then I don't know. I don't know. Minus 33, and then but just tell me the answer. Somebody will check for you. Oh, I thought you'd say you got it. Huh? Who got AB? What's AB? Huh? Minus 17. Then 16. Minus 8. 8, okay. Minus 16. Minus 8. BA? All 0. 0. In? Huh? Oh, second one is 13. Minus 7. Minus 11. 9. Minus 11. 11.
13. You're 13.
30. Does everyone got this or not? Different? All different answer. And if all different, it's a bit dangerous. Okay. Let's see. Okay. If all different, then it's dangerous a bit. Okay. Let's try. Okay, let's try. Okay. So what is AB? So let's see what I do. Okay, so what I do for the first column, first entry is I take the first column, I get 3 times minus 2, and then plus 4 times 1, plus 5 times minus 3. Okay, and then the second one would be I change the column here, so still the first row, but the second column. Maybe I just, okay, let's just write down for the first time. Really writing it down. So the first is 3 times 3 plus 4 times minus 5 plus 5 times minus 1. The second row is minus 2 times minus 2 plus minus 1 times 1 plus 7 times minus 3. Fourth one is minus 2 times 3 plus minus 1 times minus 5 plus 7 times minus 1. Okay, so you add this up. Minus 6 plus 4 is minus 2. Minus 2 plus minus, okay, minus 17, correct. How about the column one? 4. 4 minus 1 is 3. 3 minus 21 is minus 18. Isn't it? Is it? Minus 18? Okay, good. 9. 9 minus 20 is 11. Minus 11. Minus 11 minus 5 is minus 16, correct? Minus 6 plus 5 is minus 1, minus 1, minus 7 is minus 8. Okay, so this one is minus 8. Okay, you want me to do BA or can you try BA again? Huh? Okay, try check BA. Check your. And I will provide in the lecture note later. Okay, next. That's this one skip. You can try if you want, but I will skip. Try if. Okay, next thing is this is the part that makes matrix and algebra. Okay, this is the linear algebra. Okay, so The algebra here is because we can add matrix together, we also can multiply. So there are two operations here. Like what we learned in the discrete math, we learned the Boolean algebra because there are two operations. Similarly, for matrix, we have two variables, okay? And not two operations. Okay. So here now is the operation here is matrix multiplication. Okay. A, B. So you got n times n, n times p, p times something else, r maybe, size of matrix. So first, you also have multiplicative associativity. So you can multiply the first two first, or multiply the second two is the same. First is the same. Okay. So anywhere you want, any tree you want, how you want to multiply is your business. Okay. Never mind. It's the same. Second is distributivity. Okay. So you distribute your matrix. You distribute the multiplication into the addition. Okay. Next is you distribute the other way, also distributivity. Then you distribute where you add first and then you multiply. It's the same as you multiply first and then you add them. Second one is the scalar multiplication. Okay, so you can see that this scalar can run out all run into the matrix multiplication. So you can multiply R with A first, or you can multiply R with B first, or you multiply AB first, then multiply R. Okay, this is due to the commutativity of real numbers. Okay, this is not always true, but in real number, this is true because number can just swap. Second is the identity function. So remind you what's the identity function is the one on the diagonal. Okay. So in this case here, right, this A is a special A. It's a M times M. Sorry, it's an M times N. Okay. So you can realize that this M and N is different. Okay. M and N can be different. So on the right, you can multiply with the M size, and then on the left, you can multiply with a N size. So for example, in this case, we can do something like this. 6, 1, 0, 5, 6, 7. Anything. So like 0. And then this size has to be 5, 1, 2, 3, 4, 5. Okay. So the whole thing combined will be just A itself. So left and right, make sure you have the right size of identity matrix. Okay. Not very important, but this is some property you can see. Should we do this? Okay, we don't want to do this. Maybe we change this matrix to this. I'll let you see something. So what's the cube of this thing? Cube of the diagonal matrix. What's the cube of this diagonal matrix? Into what? 1. Why? Why change into 1? What change into 1? So what's this? 2 to the power 3. No? Any idea? Any idea? What's this? Any idea? Any idea? What's this? You can try and compute if you want. Just see if anyone know. You can try and compute this. And try and compute. Anyone got it? Anyone get it yet? The power of diagonal matrix, what do you get? What do you get? Anyone have done the calculation? Anyone done calculation? Done? Have you got it? Do you get anything? What do you get? Huh? What? Oh, is that? What oh is that? Okay. What oh? You mean all like this? Okay, what the rest get? You also get that? Zhao Ling, you also get this? You also get this? Seriously? You make my life questionable. Okay. Wow, so many eggs, a lot of money. Okay. So when you square it, what do you get actually? You get when you square it. Okay, when you square it, what do you get? You take the first row and the first column, what do you get? 4, correct? That's right. First row with the first column, what do you get? You sure? 4. 2 times 0 plus 2, 0 times 2 plus 0. Right? So you get 0. Okay. How about the third one? 2, 0, 2, right? Because 2, 0, 0 with 0, 0, 0, 2. And so they break up. So you get 0. How about this one? 0, 2, 0 with 2, 0, 0. You get 0. 4, 0. Okay. 0, 0, 4. Okay. And then, so in the end, you get 8 on the diagonal. So that means when you do diagonal matrix, power of diagonal matrix, you are like just taking the diagonal to a power. So you're like not doing the matrix multiplication. You can just, what you can do is you just do the power on the diagonal. Okay, by ignoring the others part. Okay, so this is the special part of the diagonal matrix. So sometimes we like to look for this diagonal matrix. Okay. Yeah. So it's like just doing the normal arithmetic instead of a matrix multiplication. Okay, next is transpose. So transpose means you you swap the entry on the row to the column. Okay, what do I mean by that? Okay, so you swap the ij component of your matrix. So for example, okay, so for example, you swap the row to the column. Okay, first row become a first column, second row become a second column. So what you do is 1, 0, 1, 2, 0, 3 will become 1, 0, and 2, 3. Okay, because what is going on here? So for example, we have 1, 1, 1, 2, 1, and 2, 2. Okay, so if we take transpose, we will get A1, 1, and then become A1, 2, 2 and 1 swap, so become 2, 1, and then A2, 2 swaps. Okay. Okay, so you row become column, row become column. Okay, for transpose. So maybe we don't want to do this exercise. You can try at home. I will provide solution. Okay. Yeah. Okay. Next is how this transpose interact with the addition and multiplication. Okay. So if you take transpose twice, you go back to your same matrix because you take a row become column and then you make the row become column again. So you swap it back. So if you do twice, you go back to the same matrix. And then second is if you add two matrices and transpose them, actually is the same as you transpose them individually and then add them together. So that means the transpose can distribute in. Okay. And if you don't believe, you can go and try some example and then see how it is true for general cases. Next is this one I think is pretty obvious because if you multiply by R, every entry already got R. You just swap row and columns. It's the same as you swap first and then multiply everything with R. Then this one's very obvious. Fourth one is a bit counterintuitive. If you do AB multiplication, transpose it, it's the same as you invert the multiplication of BT and AT. Okay, so because usually you might think, could it be this? So this one is wrong. Okay, so you need to swap the order. Okay, it doesn't just transpose, doesn't just distribute it. Okay, so this is a bit special here. Okay, yeah. So this is the thing you need to take off for matrix. This is the special part. Okay, let's see how many we think we have. Okay, maybe later will be quite long, so let's break for a shorter time so that we can leave earlier if possible. So let's stop for, let's come back at 11:06. Okay.
那个就是小分区的就这一层小一起，是啊。
我也没有钱，没钱，那请他去签。
我不知道，我是明天开始。
明天。
已经签了，
帮他签了，他不知道，
对呀、怎么签了不知道？不知道。
又有人帮他签，
那个买是和单设什么？这个凹凸了，
啊，对，什么意思？
这个没看懂。
我没看懂。满色嘛，你说满嘛，哪里满呢？满就是要满在 code domain 那里，就是每一个 code domain，就是在它的就 OK，对，这个是 domain，就每一个这里的东西，你都可以找到一个东西可以送过去。你看，就是他把这里都填满，就是我只要这里的东西我全部 map 过去，我就把它填满。
然后单设就是
单设是
只有
单嘛，
一个，
单就是说就一个，这里就一个东西被送去 B，不可能有比如说 Y 再送去 B，那就单个。
只有一个对应的是吧？
对，
那即使有的东西没对应上，它也是单设的。
也对，对，这期有印象吗
有印象，但是
？OK，
我来过。
OK，没事。我为什么就这个所有人直接从这里读出来？
啊，所以不行。
哦，这个是错的，我刚才已经说，我刚才说是错的。哦，为什么只有一个啊？就是假设，因为我这里说，如果不是的话，会有我就可以加 homogeneous。对，如果你试下你去解这个 homogeneous system 出来的话，你这边是不是全部会拿到0？
对，
这样你是不是 S1、S2都等于0？
对，
所以你 S1、S2等于0加上这个 solution，是不是还是这个 solution？这样是不是只有这个 solution？所以你这个 case 其实这个 linear transformation 是 one to one。
就是它 x 有
呀，S1、S2是0啊
不是这个
啊，是0。
另外一个只有0。
对，所以这个东西其实是 one to one。
这边的 R2和R3是的。
R3是它的这个 space，它的 domain 我的世界和 code domain，就是说它可以它的 input 是一个 R2的 vector，然后它会吐出一个 R3的 vector，这个，所以你看 R 这个 A 乘了 R2，它会给 R3。
这边2是那个 range。
range 活在 R3里，你看 range 活在 code domain。所以 range 是这一边的东西 ，image 也是这一边的东西 ，code domain 是这一边的东西。
2是2D，3是3D。
哦呀，对，R2是，对。
Everyone sign this yet? Ready sign? Ready sign? Okay. Okay. Next, matrix algebra. So we want to find the inverse of a matrix. So what's the definition of inverse of the matrix? So inverse only defined on the square matrix n times n. Okay. And m times n matrix is invertible if there exists a matrix, another n times n matrix, okay, such that if you multiply it on the right, you get the identity matrix, okay, the one on the diagonal matrix. And if you multiply on the right, you get the identity matrix as well. So on the left, on the right, everything you return to identity. Then this is called the inverse matrix for A. Okay, then we will call A invertible. Make sense? Okay, then we'll call A inverse. So A inverse is the thing that apply to A. On the right, you get identity. Apply to the left, you also get an identity. Okay, make sense? Okay, so let's try and compute AC and CA. What do you get? AC and CA, what do you get? What do you get? AC and CA. You get identity matrix. AC, you get identity matrix. Sub of CA, you also get the identity matrix. Okay, so that means this C satisfy AC equal to identity and CA equals to identity. So this means what? This means C is the inverse of A. Okay, hence A is invertible. So invert is like you turn something around, right? So you turn it become identity. Okay, invertible. So it's invertible and A inverse is C, which is -5 -3. Okay. So okay, invertible. Okay, so you might wonder how, given one matrix, how do you find the matrix? How to find the inverse of the matrix? Okay, so how to find? Okay, what's the next bit? Okay, so determine when is a 2 by 2 matrix invertible. So maybe let's see when is a 2 by 2 matrix invertible. Okay, so let's see. Let's set A equals to A, B, C, D. Okay, let's set A equal to A, B, C, D. And then we want to find when is this invertible. So when A is invertible, then there exists P x1. Let me see, what do I set? S1, S2, S3, S4, another matrix such that AC equals to identity and CA equals to identity. Okay, right? Make sense? Okay. Okay. So what do we have here? So we have A, B, AC equals to AB, CD times C1, S3, S3, S2, S4, and equals to the identity. Okay, we want to find a solution again. Okay, but now this solution is like a matrix hiding inside the matrix. Okay, so from this here we can get 4 linear equations. Okay, can you see it? If not, we try and expand it. So first one we get AX1, how to multiply matrix, plus BX3. Okay, AX2 plus bx4. Okay, everyone follow like this. Again, and then like this. First row, second column, and then second row, first column, and then second row, second column. Right? Okay. So from here you can obtain 4 equations. Okay. So what's the 4 equation? X1 plus x3 equals to 1, and then x2 plus bx4 is equal to 0. Cx1 plus dx3 is equal to 0. Cx2 plus dx4 equals to 1. Okay, so you obtain a system of a linear equation. Okay, so when does C exist? What should you do? What should you do next? How to find the solution? What do you do? Huh? What do you do on the first day? What do you do? Huh? Any idea? What do you do? What do you do? You got a system of linear equation. Transfer it into the augmented matrix and then row reduce it. Right? So what's the augmented matrix? Because you want to find the solution, right? So what's the augmented matrix? Is A x1 plus 0 x2, B x3 plus 0 x4, and then 1 here, and then 0 x1 plus ax2, and then 0 x3, bx4, 0, C, 0, D, 0, 0, 0, C, 0, D, 1. Okay, everyone can see how to transform. Okay. Any question? Yeah. No? If not, then we will do the row reduction together here. This row reduction a bit tricky. Okay, we want to find solution, right? We want to find C. We want to find all these variables. Okay, let's row reduct. Yes. Reduct this. Okay. So if we want to find a solution, okay, solution to this system, meaning I need to have pivot position at every row. Okay, so we need to check whether we have pivot position at every row or not. So what we can do, what I do is I want to make the pivot position. I want to make the first A to be the pivot position. So I need to make C disappear. So what I do is, let's see, do is A times R3 minus C times R1. Okay. And then I also want to make, because there's no overlapping on the second row, so I can do them together. So I want to make a second A pivot position as well. I need to disappear C the same. Okay, before that, can you see that there's some symmetry here? AB, AB, CD, CD. Okay, really, we can do the same row operation, similar, not the same. Okay, so for example, we can do AR3 minus CR1 and AR4 minus CR2. Okay, so let's see what happened to R3. Okay, and then we keep R1 and R2. So we can keep R1 and R2. Okay, what is R3? AR3 minus CR1, you get 0. Okay, 0 times 0, 0 times anything, 0. So how about this? AR3, so AD minus CB. Okay, everyone follow? Okay, and the next part is 0 again, and then 0. And the next part is C, similar, we get A Did I do something wrong? Okay, no. This one is 0 because AC minus AC, you get 0. And then you get 0. And then AD minus CB again. And then here, what do you get? You get A. Okay, I did something wrong here. Here, what happened to here? This is minus. No, yeah, minus what? Minus C. Correct. Very good. Oh, this one is minus C because this pick up the minus C. Yeah. Okay. Good. So you can see that here, this one. Okay, we want pivot column at every place here. So that means AD minus CB cannot be 0. Okay. A also cannot be 0. A can be 0. Okay, A depends because got B. A and B cannot both be 0. Okay, you can see that A, D cannot be 0. Okay, so that you don't have 0 rows. Also, A cannot be 0, I think. Yeah. Okay. So it is invertible when A and B is not because A or C is not equal to 0. C. Okay. Because if A and C both 0, then this thing will automatically 0. Automatically 0. Okay. So either C cannot be 0 or A cannot be 0, and also AD minus CB cannot be 0. Okay. If you remember, right, this one is actually the determinant of your 2x2 matrix. 2x2 matrix. The determinant of the matrix. If not, never mind, but just take note of this matrix here. Okay, so we have determined when it is invertible. Can we reduce to row echelon form? Okay. If we reduce to row echelon form, what does it mean? What does it mean by I reduce to row echelon form? What's the solution give you? What does the solution give you if I reduce this matrix to row echelon form? What does the solution give you? It solve this matrix equation here. Okay, meaning it calculate the A inverse for you. Okay, make sense? Yeah. So let's try and row reduce it. See what's the x1, x2, x3, x4 in details. Okay. So let's row reduce it. Row reduce it. What's the next thing I do? Okay, the next thing I do is I take row 2 minus B of AD minus CB R4. Okay, why I do this? Because I want to get rid of everything above the pivot position. Okay, before I scale it. So I get rid first. R1 minus B over AE CB R4. Okay. Because if I want to get rid of this B, right, I need to make this into 1 and multiply B. So that B minus B is 0. Okay, makes sense? Okay. So what I get here in the end is, you can check my answer. What's the end I get is C over AD minus CB 0 A 0 0 minus EA over AD minus CB 0 0 AD minus BC 0 0 0 AD DB. Okay, why? You can see that here is 1, right? 1, what happened? 1 minus B over AD minus CB. Did I do something wrong? Okay, yeah, here is R3, sorry. So this one, because I want to cancel this B with this one, okay? So R1 and R3. So 1 minus C, okay? So I got BC over AD and CB. Okay. Similarly, for the second row, so second row, I cancel the B with the row 4. So what I have is 0 minus B times A over AD minus CB. So I got this. Okay. Okay. Any question? No? No question? Following? Okay. Okay. So what's the last step to do? I just need to make the leading entry into pivot position. So I just scale everything. Okay. So if I scale everything, what do I have? Okay. Before that, what is this? What's this? Can you simplify this? What's that? What's this? Equal to AD minus CB plus BC over AD minus CB. Okay. So this part is just AD of. Okay. So this part is equal to AD minus over AD minus CB. Okay. So you divide A from the first column, you divide A from the second row, and then you might divide AD minus BC from the third row, and then you divide AD minus BC from the fourth row. Okay. So what do you have? You have 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. Okay. And then you get D over AD minus CB. And then second, you get minus B over AD over CB. And then third row, you get minus C over AD minus BC. And then fourth, you get A over AD minus BC. Okay. Okay. So you just do 1 over A on first row, second row, and then 1 over AD minus BC on the third row and fourth. Okay. So now what do you get? You get S1, S2, S3, S4. Okay. Maybe it might seem very messy. Okay. But you can see that when we organize them together, okay. So from here you can read that D equals to AD minus CB. X2 is equal to minus B over AD minus CB. And S3 equals to minus C over AD minus BC. And then S4 equals to A over AD minus BC. Okay. Then you can arrange them into the matrix C. Okay. How do we start off with C? C is X1, X2, X3, X4. Okay. So you put this number in appropriately. So what is it? Let's put them in. So let's move this. Okay. So move the 2 to this side. Move the 1 to this side. Into this side. Okay. Did you notice anything? What do you notice? What do you notice? Huh? What do you notice? Can you say what you notice? Huh? X1 multiply X4. And then equal to 0. What do you mean by that? Okay. What I want to say is they are all divided by the same denominator. Okay. So you can pull the denominator out and then you will get this inverse formula. Okay. So in discrete math, I didn't prove it, right? I mean, we did this in the tutorial, but today this is the proof on how you find the inverse matrix for 2x case. Okay. So in summary, how do you find this inverse? So Let me put this inverse back and then we compare with M. So C is equal to 1 over AD minus C B, then D A minus B minus C. Okay, so what's the inverse? So this you can memorize is you can swap D and A and then put minus on B and C and then divided by the determinant. This is the inverse of A for 2 by 2 case. Okay. And this formula is very important because this is how we generalize to higher dimensional case. So this one is very important, and then we find it just from row reduction method. Okay, so this one is very important. Okay. If you wonder how this formula come from, you can use this way to find it. Okay. Any question? Okay. Okay. So you might wonder whether it is true because I only calculate AC, right? Maybe you ask, how about CA? How about CA? CA. How about CA? You can try. It's the same. Yeah, you can try out CA. Maybe let's go. By row reduce CA. CA equal to 2, yeah, 80. Okay. You should get the same result. There's a note here. If a matrix is invertible, then the inverse is unique. Okay. Unique meaning there's only one. Okay, there's only one. Okay, so let's try and use the formula to find the inverse of A. So what's the formula? Remind ourselves again. If A is A, B, C, D, then the A inverse would be 1 over AD minus BC times swap D and A, and then put a minus on the other diagonal. Okay, so what is A inverse? 1 over AD minus BC, what do you get? 9, 6, 54, 54 minus 56, minus 2, is it? Minus 2? Correct? 9, 6, 54, 52, yeah, right, 56, 54, correct? And then E 96 and then 7, 8. You get this? Get this? Okay. If you want to check, you just take your A and A inverse and then check whether you get identity or not. Okay, multiply A and A inverse to check whether you get identity. Okay. Okay, so why are we doing this? Why are we doing this? Why are we doing this? Let's say we want to solve this linear system. Okay, solving linear system again. So what's the matrix you need to get? The augment. Okay, not augmented matrix, but this one. What's the matrix equation to this? What's the matrix equation? So you read out the coefficient. X1, X2 equals to 1 minus 2. Okay, remember? Okay. So can you recognize this matrix here? This matrix is the same matrix here. Okay. So let's denote it as S AX equal to B hat for the moment. Okay. Let's say we know the inverse of A. So we can put A inverse here. A x bar equals to A inverse on both sides. Okay. What do we get? I get identity on the vector and A inverse B hat. Okay. And then what is identity on the vector? Identity matrix on the vector. You still get back your vector. Because remember, vector is also a matrix. Okay. So you get back your vector. So what you need to do is you don't need to go through the row reduction again. So you just take the inverse matrix you found, multiply the constant vector. Okay, so your solution will be taking the inverse matrix, multiply the constant vector. Okay, then you get your solution. You can compare the solution with the one that you do using row reduction. Okay. Yeah. Okay. Much easier. Okay. But only when the inverse exists. If the inverse doesn't exist, then you cannot do. Okay. All right. So the next theorem is if A is invertible, if A is an invertible matrix, then the linear system has a unique solution. You can see that if you multiply it, then you will get only one solution. Okay. Or if A is invertible, the linear system has a unique solution. So this means A is what? From last hour. If A is invertible, then A is 1 to 1 or 1 to 1 to 1 or 1 to. A is 1 to 1 because there's a unique solution. Okay. So there's only one get mapped to B. One image get mapped to. Okay. In other words, A is 1 to 1. Okay. Okay. Yeah. Actually, it is also 1 2, but more directly to see is 1 2. It is also 1 2 actually. But anyway, next. This one I'll leave it to you. Later I will provide solution. You can do it. And this one leave it. This calculation. See how transpose interact with inverse. Okay. And then how inverse interact with product multiplication. Okay. I'll tell you the result. So if you inverse twice, you get back yourself. Just like transposition, inverse. This is similar to number, right? So you invert a number and you invert again, you get back 2. Okay. Yeah. Okay. So it's similar to number, which is what we want. Okay. Next, this one also follow the same trend from the transpose. If you invert the product, okay, it's the same as you invert B multiply A inverse. So you change the order of multiplication. It's the same as transpose. Okay. This part is a bit counterintuitive, but this is the property it has. Okay. And then how about transpose and inverse? You can swap them. You can do the inverse first or you do the transpose first, it's the same. Okay. Where you can verify it using this example if you want. Okay. Okay. Yeah, that's all for this one. Okay. Any question up to now? Any question up to now? No. All good. So far, so good. Okay. Next, we will introduce elementary matrices. So the first time you heard about elementary is the elementary equation, elementary equation operation and elementary row operations. Okay, so these elementary matrices are related to those three operations. Okay, actually, those three operations you can realize as matrices as well. Okay, so remind you what is the three row operation we have. We can interchange row, remember? Okay, what else we can do? We can scale a row. Okay, we can replace a row with a sum and a scalar multiple of the other rows. Okay, so let's see what these three refer to, which properties. Okay, let you compute this. Try and compute E1 on A, E1, E2 on A, and E3 on A, where A is the string. Okay, let's see what these three matrices does to A. Okay, try and see what you have. Try and see what you got. Take E1 multiply A, E2 multiply A, E3 multiply A. Try and see what happened to A. Okay, try and compute this matrix multiplication. Done? If done, you can check the answer with me. Okay. If you still doing, just give you a bit more time. Okay. Okay, let's check. Let's check the answer. If you haven't done, you can look up here. So what E1 does to EA? Okay, you can see that A, B, C appears in row 3. Okay, and then with the scalar multiple of -4. Okay, so this means this vector have replaced row 3 with the sum of -4 times row 1 plus row 3. Okay, so you should see this elementary matrix how it differs from the identity matrix. Okay, because identity matrix will do nothing on the vectors. Okay, so if you add a 4 at a random place other than the diagonal, you will do replacement. Okay, if you, how about you swap the row of the identity matrix? You can see that if you swap the first and 2, which is E2, you also swap the row of A. You can see, can you see or not? A, B, C become the second row, and then D, F become the first row. Okay, so if you want to do swapping, you just swap the row of identity matrix. Next one is if you change the number on the diagonal, you will scale the corresponding row. So if you change the third row, you will scale the third row. Okay. If you scale the second row, then you will scale the second row of the matrix. Okay, so that means what you do on the row operation, really you are doing matrix multiplication. Right? So everything can be phrased into matrix multiplication. Okay, all the process. Make sense? Okay, so secretly you are doing matrix multiplication. So what's theorem stating here is if an elementary operation is performed on matrix A, usually we perform on the augmented matrix. The resulting matrix can be written as EA. So a sequence of EI putting together. So when you, okay, we give you a picture. So every time you do this row reduction, right? Okay, so you are multiplying some EI here. Okay, and then you can go all the way EI. So sorry, should be on the other side. EI, EJ, or E something, EN on A until you get the row reduced echelon. Okay, so you get the row reduced echelon. Make sense? Make sense? Okay. 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 What's next? Okay. Next theorem is each elementary matrix E is invertible. This one to prove, maybe not so hard to see. And the inverse of E is the elementary matrix of the same type that transform E back to C. E back to identity. This one is not hard to predict, okay? Because if you add row 4, if you scale a row, how do you make it back to the same row? You just scale by 1 over the factor you're scaling. You get what I mean? You get what I mean? So let's say you have something like this. Zero, 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 5. So the inverse should be scaling back 1 over 5, correct? So you put 5 and then you divide by 5 again, so that you get back the same equation. Okay, so they're both scaling. And then if you want to interchange row 1 and row 2, how do you change it back? How do you change it back? You change row 1 and row 2 again. Okay, so they are the inverse. So this one is inverse. Okay, it's interchange. Okay, similarly, replace. So for example, just now, what do we have? -4, 0. Okay, so you already did -4 R1 plus R3. How do you turn it back to the original R3? Okay, so one easy way to see from algebra is, let's say I set this thing as your new R3, Okay, I want to find OR3. How to find? So I just put the R1 to the other side. Okay, so in this way, I can find my OR3. This is a new R3. So the inverse will be 1, 0, 0, 0, 1, 0, and 4, 0, 1. Okay, that's all. You can test it. If you don't believe me, go and verify. Okay, meaning go take this one and multiply with the matrix, see you get identity or not. You get identity. Yeah, I let you try out and you let me know. Okay. This in general, this one need to prove, but I'm showing you show example for second statement. Okay. Because if you already found the inverse, that means it is invertible. So second statement is very important here. Okay. So if you can find the inverse, that means E is invertible. This is one way to prove it. Okay, next step is to find the inverse. Okay, I already find it. So we can skip this. Yeah, yeah. Or I already find it for you. Yes, 1151. Let me see. Oh, okay, one last thing before we end. Okay. A theorem here is n times n matrix is invertible if and only if it is raw equivalent to I to the identity matrix. In this case, any sequence of elementary raw operation that reduces A to identity matrix also transform A inverse A identity to A inverse. Okay, so there's some content here, but what does first thing mean? So I think we won't prove this, but how to understand the first one? So to check a matrix is invertible. Okay, what you can do is row reduce it. Okay, row reduce the matrix. Okay, see if it is see if it can be reduced. Okay, see if its raw reduced echelon form is identity matrix. Okay, if it is an identity matrix, then by definition it is by theorem, it is invertible. If it is not, then it is not invertible. In particular, if you found free variable in your row reduced echelon form, then the matrix is not invertible. Okay, so you must row reduce until identity matrix. So that means something like this. Okay. And in this case, the sequence of elementary row operation that reduce it will transform it into A inverse. I will transform identity into A inverse. Okay, how to picture this? For example, if you perform some elementary sequence of elementary row reduction, okay, until identity, okay, then what you can do is you take the whole thing here and then find the inverse. Three, one, inverse. and then the holding here. Let me size and then take it here on both sides. Okay. Then on the one side I get AI equals to the whole thing. Copy. Okay. A is actually equal to the inverse of this. And the inverse of A is what? Inverse of A is just the product of the sequence of the elementary rho reduction. Besides this. So if you can rho reduct to an identity matrix, you take the product of this elementary rho reduction. This is a matrix that multiply A, then you get the identity. Okay. So to get A inverse, you just multiply. You just what? Just take the product of the sequence of elementary rho reduction operation you get. Can understand? Okay, never mind. We will continue next week because time's out, and then I will show you this algorithm. Okay, I'll show you this algorithm how to find A inverse next time. Okay.哦，这个 E 是那个 elementary rho operation 的一个 sign 的 sign，可以用 sign，就是你 rho reduction identity 啊，什么？就是当你做 rho reduction 的时候。你一直做，直到你得到一 ，OK，好，拜，对不对？对不对？所以每一个那个 elementary rho operation 都可以用一个 matrix 来表示，记得吗？来，这个啊 ，OK。所以当你在做每一步 rho reduction 的时候，都是一个 elementary rho 都是一个 elementary matrix。所以你把所有的步骤组合在一起，是不是还是个 matrix 乘 matrix 嘛？对不对？发一下啊，发。我会发。不是发了，你知道我在写什么吗？凭感觉没有，下周还会再说。但是就是你把所有的步骤还有那个 matrix 乘在一起。周三呢，我还没拿到quiz，我会再公布一下。